Yes. Will this work? Yeah. Thank you.
So no laser pointer, just
All right. Thank you. So my name is Ronak Ramachandran, and I'm presenting joint work with Blake Holman and Justin Yurka on quantum search with in-place queries. So search is ubiquitous, from doctors trying to find medical records to researchers trying to find the theorem that proves, a proof they're trying to resolve, to hackers trying to find your password by inverting its hash. And in all these cases, at its core, search is a problem of function inversion, where the domain of the function that you're inverting is the space that you're searching over. Uh, for all items that you want to find, your function outputs 1. And so searching is just finding the preimage of 1, or sometimes finding a specific element within the preimage. And so it's important to know how much time it takes to solve this problem, but time is hard to quantify, so we often use query complexity as a proxy for time. So what is query complexity? Well, we imagine that our only way to access our input f is as a black box, and we can ask questions, we call queries, of the form x, and receive back answers of the form f of x. And each question is expensive, but everything else is free. And the query complexity of a problem is the minimum number of queries necessary to solve the problem. So now, how can quantum computers make queries? Well, to perform a query, we need to be able to transform x to f of x within a quantum circuit. And quantum mechanics is reversible, so quantum queries need to be reversible. But this poses a problem, because if f is not reversible, then the map that maps x directly to f of x is not unitary. And so the normal way to get around this issue is something called the XOR query, where we take the output of our question and we XOR it into a second register. And this is now invertible, because if you just query again, you get back the original state XA. But when f is a permutation from n items to n items, that is when it's a bijection, then this original map we were considering from x directly to f of x is unitary. And so we can consider the following kind of query, where we directly map x to f of x. And the central question of this talk will be, given some permutation f, how do XOR queries and in-place queries to f compare? So first of all, classically, there's no difference between these two. And even quantumly, if we have access to both f and f inverse, then the two query types are equivalent because they can simulate each other. But if we only have access to f, then in-place queries look very powerful. And so there was this work of Kashefi, Kent, Vedral, and Banashek, where they showed there's an f, a specific f, that has XOR queries that are easy to implement with quantum circuits, but in-place queries to f would efficiently solve a version of graph isomorphism. And so if we could generically simulate in-place queries with just a few XOR queries, then we would place this problem in P, which is something that isn't known yet. Fortunately, or maybe unfortunately, Kashefi et al. Also proved that at least root n XOR queries to f are necessary to simulate one in-place query to f for all f, well, generically. And so this eliminates this, this possible way of solving graph isomorphism in BQP. So the question still remains, the question that you might consider is, are in-place queries stronger than XOR queries? And we have lots of evidence of problems that require fewer in-place queries than XOR queries. And prior to this work, there was no evidence to the contrary. But at the same time, XOR queries and in-place queries were believed to be incomparable. And the leading candidate for a problem that required more in-place queries than XOR queries was unstructured search, which in the case where f is a permutation is called permutation inversion. And this requires root n XOR queries by Grover's search algorithm. But in 2018, Pfefferman and Kimmel conjectured that you would need at least order n queries to an in-place oracle in order to solve this problem. And in this work, we refute this conjecture by providing an algorithm that uses only square root of n in-place queries to f. So the question still remains, are in-place queries stronger than XOR queries? We eliminated the leading candidate problem, but are there other problems that could provide the desired separation? And so we define a state conversion task, which we call function erasure. It's analogous to index erasure if you've heard of it, where the goal is to take classical states of the form x f of x and transform them into x 0. So we're zeroing out the function register. And this is possible with one XOR query. You simply make the query. But this, we prove, requires at least root n in-place queries. And this is the first example of a problem requiring more in-place queries than XOR queries. So in this talk, we're going to cover a couple things. First, we're going to go into why Grover's search algorithm fails if we try to use in-place queries. And the answer is going to be function erasure. And next, we're going to go into our search algorithm, which uses only square root of n in-place queries. And finally, we'll prove that root n lower bound for function erasure using in-place queries. So first, why does Grover's search fail when you have in-place queries? So as a review, this is how Grover's algorithm works. You start off with an equal superposition of all classical bit strings. And first, you query f, which means you negate the amplitude on the marked element x star that you're searching for. And then you diffuse, which means you flip all of the amplitudes about their average. And you keep alternating these two steps of querying and then flipping about the average until you've increased the probability of measuring your marked element above a constant. So where does this break with in-place queries? Well, it breaks during the query step. And so what we're trying to do during that query step is we're trying to apply this negative phase to our marked element, the element where f of x equals 1. And so we can write that succinctly as follows. And if we try to accomplish this with XOR queries, the typical way to do this is we start off with x, we introduce an auxiliary register initialized to 0, we apply our XOR query to get f of x, then controlled on that second register being 1, we apply a phase, and finally, we apply an XOR query in order to erase that second register. And this last step here is exactly function erasure. And as we'll prove later in the talk, function erasure requires at least root n in-place queries. So next, how do we fix this? How do we search with in-place queries and recover the Grover speedup? So without phase flips, what can we do? Well, note that the main operation that in-place queries do is something we're going to call a shift, where because the in-place query takes f to f of x, then the amplitude that was previously on f inverse of x will then be shifted onto x, and the amplitude that was on x will get shifted to 1. And so this is the action of an in-place query. So can we use this in order to move amplitude onto the marked item so we can search for it? And so our goal is to mimic one iteration of Grover search, or more precisely, we want to increase the amplitude on our marked element x star by at least 1 over root n with just a constant number of in-place queries. And then if we accomplish this, then we can just repeat this procedure root n times in order to get a constant amplitude on our marked item. So the way this is going to work is we're going to start off with a superposition where it's uniform on everything but our marked item. And we're imagining we have this alpha amplitude on our marked item. And initially, all of these will be 1 over root n. But as you'll see in the analysis, it'll be helpful to have these variables. And so what does this look like? Well, if we're partially through our algorithm, x star will have a little more amplitude than everything else, and everything else will have some small beta amplitude. So alpha is represented by the yellow bar, and beta is represented by the gray bars. Next, what we do is we introduce an auxiliary register initialized to 0. We XOR the first register into the second register in order to get 2 copies of the classical information. And then we apply an in-place query to that second register. And note that because our marked element is marked, f of x star is going to be 1. So that's why there's a 1 there on that second register. And now, what we would have liked to do in Grover's algorithm is apply a phase, but we're not going to do that here. Instead, we're going to introduce a flag qubit, which controlled on the second register being 1, that is controlled on us being in the branch of the wave function that has our marked element, we're going to flip that flag to be 1. And so we're going to call this the mark step, because it's like we've marked our marked item. But note that this isn't very good. We're not going to be able to interfere these 2 branches because we have garbage on the second register. That second register contains f of x. And so in order to get rid of this garbage, we might try the following. The first thing we do is controlled on the flag being 0. We're going to apply an in-place query to the first register. And it's not immediately obvious that we have access to controlled in-place queries, but in our paper, we show a construction for it. It's quite strange, so I recommend you look at the paper. Um, but then, after we've done this, we can get rid of that garbage on the second register by simply XORing from the first register to the second register in the branch of the wave function that has the flag set to 0. And in the branch of the wave function where the flag is set to 1, we can simply apply a unitary that transforms the state 1 to the state 0 on that second register. And so now what we've done effectively is on just this 0 flagged branch of the wave function, we've applied a shift operator. And we've gotten rid of the garbage. So we call this the shift step. And now let's zoom in on this state that we've arrived at and note that if we could just add these two bar charts together, then we would have achieved the desired goal, which is increasing the amplitude of x star by about 1 over root n. But how can we do this? Well, one thing we could do is we could try to interfere these two branches of the wave function. And so what we're going to do is we're going to look at the flag qubit in the Hadamard basis. And if we group terms by their state in the Hadamard basis, well, the gray bar chart will look like this. It'll get added in both branches. Both the plus flagged branch and the minus flagged branch are positive. But note that the orange bar will get added to the plus branch, but it'll get subtracted from the minus branch. And so this is great because in one branch of the wave function, we've amplified x star. But in the other branch of the wave function, we've actually dampened it. The probability of measuring x star is lower than we wanted. But note that in that branch, it kind of looks like we've done an in-place, it kind of looks like we've done a phase flip. And so what if we just apply Grover's diffusion operator here? So if we do that, we end up flipping all the amplitudes about their average, and we arrive at this state. And finally, what we can do is we can convert the flag back into the standard basis and combine like terms again. And what we'll arrive at is a state where the flag is 0, x star has been amplified, and where the flag is 1, we actually have negligible amplitude on that entire branch. In fact, we can measure the flag at this step, and if we ever see 1, we can just declare failure of our entire algorithm, and it's not going to affect our constant probability of success. Okay, and so then our algorithm is just going to be repeating this procedure where we mark, and then we shift in just the 0 flag branch of the wave function, cleaning up the garbage. And then we apply the Grover diffusion operator controlled on the flag being the minus state in order to recombine these two branches into something where x star is amplified. And we can just keep repeating these steps over and over again until x star has an amplitude that's super constant. So the probability of measuring it is high. Finally, we're going to, now that we've finished our algorithm, we'll go into why function erasure requires at least root n in-place queries. So why is function erasure hard with in-place queries? Well, the proof sketch is going to have 3 steps. We're going to show that solving function erasure with in-place queries would let us simulate XOR queries. And then we're going to show how simulating XOR queries with in-place queries would let us solve permutation inversion. And finally, we'll rely on a proof by Pfefferman and Kimmel, and later reproved by Belovs and Yolku, that permutation inversion requires at least root n in-place queries. And so this first step we can do right now. It's pretty simple. What we do is we start off with the initial state of an XOR query. We can introduce an auxiliary register initialized to 0. We can XOR the first register into the third register. Then we can apply our in-place oracle to the third register to get f of x. We can XOR that f of x into the second register. And now we're almost at the point where we've simulated an XOR query. The last thing we need to do is we need to do function erasure in order to get rid of that auxiliary register. And so here, if we have a subroutine that does function erasure with just one additional in-place query, we can simulate an XOR query. So now all that's left to complete our proof is to show that if we had a circuit that simulated XOR queries using in-place queries, then we could use it to solve permutation inversion. So how does this go? Well, we imagine we have some circuit that simulates an XOR query that uses L in-place queries to F. And we're only going to care about the specific conversion from x f of x to x 0. So we know that an XOR query is going to do this, so we know our circuit in particular will do this. And if we then invert the circuit by reversing the order of all the gates and inverting each gate, then we get a circuit that converts x0 to x f of x that uses the inverse of the in-place oracle to f. But the inverse of the in-place oracle to f is actually just an in-place oracle to f inverse. And so now if we just symbolically replace all instances of f with f inverse, then we get a circuit that takes L in-place queries to f, and it computes f inverse for any x of our choosing. And so this solves permutation inversion. And so that completes our lower bound for function erasure. So we can combine our algorithm and our lower bound in order to get some interesting results, summarize some interesting results. First, permutation inversion takes exactly theta n in-place queries. This comes from our algorithm and the known lower bound of Hefferman, Kimmel, and Belovs and Yolku. Function erasure also takes theta root n in-place queries. The lower bound we just proved, the in-place, the upper bound comes from our algorithm, a modification of our algorithm. And in fact, we can use our algorithm to also simulate XOR queries. And we get an interesting summary of the relationship between these four oracles. So that's an XOR oracle to F, an in-place oracle to F, an XOR oracle to F inverse, and an in-place oracle to F inverse. Using a combination of lower bounds, our algorithm, Grover's search, we find that any one of these queries can simulate any one of the others using theta root n queries. So there's sort of this incomparability between all of the different query types. Now, for future work, note that our lower bound for function erasure was only for a state conversion problem. And so a stronger result we'd still desire is a decision problem that requires more in-place queries than XOR queries. And we have many candidates for this. In 2021, Aronson proposed Simon's problem with garbage. So this is just like Simon's problem, but every time you make a query, you get a little garbage in addition to your actual answer. And we introduce embedded permutation inversion, which is just like trying to invert a permutation, only your permutation is embedded in a much larger space. And the issue with this is that there's very few available lower bound techniques to prove the lower bound we want. We prove in our paper that the polynomial method fails, and we also show that if we were to use the adversary method, we would need unprecedented adversary matrices that to our knowledge have not been used in any lower bounds using the adversary method before. And you can look at the appendix of our paper if you want more details on these extended adversary matrices. And so the key takeaways of my talk are that search is possible with theta root n in-place queries, and that some tasks require more in-place queries than XOR queries, something that was not known before this result. Thank you for listening.
Thank you for the talk. I had a small technical question, something I didn't quite get. So when you introduced at the beginning the alpha and beta, saying that it's good for like all generality,
Right.
it seems that as you go step by step, the betas are not actually constant for all elements. Is that
Right. Yeah, so it's actually, it seems almost like excellent luck that it works out. So yes, we assume at the start that all the betas are the same for everything other than our marked item. And it does look like later in the algorithm, at around this step here, it seems like we have no amplitude on 1 and we have like higher amplitude on 1. When we end up averaging these two in the branch of the wave function where the flag is 0 at the final step, it actually turns out, the math works out such that all the betas are the same because the average of that 0 in the branch on the left and the increased amplitude of the branch on the right ends up averaging out to be the same as the rest of the betas. So that assumption at the start that all the betas were the same holds. Yeah, good question.
Thank you. Great talk. Can you go forward a bit to that picture with the bidirectional arrows and the P's and such?
Yeah, absolutely. Whoa. There we go.
Yeah, I'm just wondering, can you restate the meaning of this picture?
Yeah. How come it's not playing? Oh, wait. Give me a second. There we go. The meaning of this picture.
Yeah.
So it's just like if you have, let's say, SF, which is an in-place oracle to F, and you have PF, which is, sorry, SF, which is an XOR oracle to F, and PF, which is an in-place oracle to F, the arrow from SF to PF would represent the idea that if we wanted to simulate PF with SF, we would require root n queries, and also that root n queries would suffice, and vice versa with the alternating arrows. Yeah,
Thank you.
no problem.
Yeah, thank you. A short question. Maybe you mentioned, does it work with more than one marked item as well for the search?
Right. So when you're doing permutation inversion, sort of by definition, there is only one marked item because there's only one element that gets mapped to one. But this is you could try to think of ways to generalize this. So for instance, you could say like, can you invert this subset? So just like anything that on the first, I don't know, 10, like the indices from 0 to 10, what is the inverse of those? We haven't looked at that in this work, but that's a reasonable thing to ask, and we could try to.
Makes sense. Thanks.
Yeah.